in this lesson, we're going to use the data that we collected on page 129 and do some math calculations with this data. And our overall goal for the entire lesson is to answer this question: how does calorimetry use the conservation of energy to collect system data? So on page 129, we answer these questions from this website, and then we use this simulation to collect data for unknown sample metal 1, and we're going to identify what unknown sample 1 is using our data here. On the top of page 130, you should have this information copied down. This is all the information that you need for doing math for calorimetry or thermochemistry. So E symbol is for energy, lowercase q is for heat or for energy. Sometimes you'll see it a capital Q. I added that. It's a typo. It should be lowercase, but you'll see it both ways, so I just want you to be aware. Capital H is enthalpy, which stands for heat flow. The triangle is change in, and it's always final minus initial. It could be change in enthalpy, it could be change in temperature, it can be change in anything. That's a delta sign. It always means change in. The lowercase m is mass, capital T is temperature, capital C stands for specific heat. If you have negative Q values, those are exothermic, and positive Q values are endothermic. So we're going to work with this quite a bit, because your negative numbers don't mean it's less than 1 or 0, sorry. It literally means that it's endo or exothermic. So those mean different things now. All right. Over here, the units, joules is the unit that you're going to have for Q, for heat and energy. You'll also find calories is a similar unit. These two things are like Fahrenheit and Celsius. They're one and the same. Specific heat has all those three combined, right? It'll be joules, grams, degrees Celsius, or calories, grams, degrees Celsius. There's a lot of variety there. The formulas is Q equals MC delta T. Also, sometimes it'll be typed like that, but again, that is a typo. And Q is equal to the change in enthalpy. Right, those two are one and the same. A lot of this is in the district packet, so you might want to check that out too. All right, this is how we're going to walk through this. And we're going to calculate specific heat of the unknown metal, and then identify what the unknown metal was that was used in the simulation. And these are directions. We're going to follow them step by step. We're going to need our data once in a while also. And I'll try to write this as neatly as possible. So step 1 says calculate the change in temperature of the water. A lot of times we'll have subscripted things because there's multiple things going on, or we have two different temperature changes, so it'll tell you what they're looking for. So delta T, right, there's that delta. So if it says delta T, it's always final temperature minus initial temperature. So I need that for water, right? So I've got to go back to my data. Oh, this is probably not the best way to do this. Let's do this. We're going to need this quite a bit. Here we go. Alright, so here's my water, and I'm going to take my final and I'm going to subtract my initial. So 24.08 minus 20. Alright, so 24.08 minus 20 is going to be my delta T. Significant figures count here, so one goes out to the tenths place and one goes out to the hundredths, so I can go out to the smaller one. So in my calculator I get 4.08. but because this one always goes out to the tenths place, I can only report to the tenths place. So 4.1 degrees Celsius is my delta T for water. Now we're going to calculate the Q, or the heat, or the energy of water. So Q water is equal to the mass of water times the specific heat of water times the change in temperature of water. So this is, we're learning, so I'm adding all of this, but if it says Q water, you have to make sure you have all your values for water. That's one place that we make mistakes, right? So I'm giving you the specific heat of water. It's also in your district packet. It's like density, right? It's not going to change. It is what it is. So we need mass, and from this, so the mass of the water was 200 grams. So Q water is equal to 200 grams. The specific heat is listed here, 1.48 joules grams degrees Celsius, and I just calculated my change in temperature. I am going to cancel out my like terms. Celsius goes, grams go, and I'm left with joules. I pick up my calculator, and I got 200 times 4.18 times 4.1, and I get Q is equal to 3427.6 joules. Now, I don't know how many significant figures were actually in this 200. I don't know if it was listed as 200. So I should have checked that. Sorry about that. We can't report all of this because either got 1 or 2. So let's go with 2, and I can check back later. Maybe 2 significant figures there. All right. Now we're going to state the Q of the metal, because heat flows, right? Sorry, and I shouldn't have done that. I got really excited with my Sharpie there. So it doesn't say calculate, it says state. So Q metal, right here, Q water is equal to the opposite of the Q metal. That's what that says. Let me get a little closer for you. Because whatever heat was lost or gained by the water is the opposite for the metal. And vice versa, right? Because we're in a system and we don't create or destroy any heat or energy. So if my Q, right, for H2O is equal to 3400 joules, that means my Q of my metal is a negative 3400 joules. And here we've got those positive and negative bits of information. And this makes sense because the water absorbed energy, so it was endothermic because the metal was hotter, and the Q metal here is negative, right? So the Q negative means it's exothermic, and the metal definitely gave off energy, and the Q positive for the water is endothermic. We calculate the change of temperature for the metal. So the change of temperature for the metal is right here. We've got the final and the initial. So delta T water is going to be 24.08 degrees Celsius minus 200.0 degrees Celsius. And that is going to be 2408 minus 200 is equal to a negative 175.92. I can't report all that. I can go out to one place because there's one place here. So that is my change in temperature. It is a negative. And the last step, we're going to calculate the specific heat. It's just a rearrangement of the other formula. So we need all metal data here. So C metal is equal to the Q metal, which I have right here, -3400 joules, divided by the mass of the metal, which from my data table is 50 grams. I'll pop this up a little bit. Focus it for you. And my change in temperature of my metal, which I have right here. So -340, well, I'd probably do the multiplying first, times, on the bottom I'm getting 8795, that's grams degrees Celsius. -3400 joules. So I get, looks like I can have 2 sig figs. Again, I'm going to have to go back and check for you. And it's 3, 8, 6. Right. So there is my specific heat. And all I need to do to infer the metal is take a look at this, and these are like densities, so I need to find the number that is closest, and it looks like this one. Therefore, zinc was the metal that they used in the simulation. Now if we go back and check, I had you write down the specific heat, which you weren't aware of at the time, and the specific heat you wrote down was this one, which is exactly what we calculated.